Dear students, welcome back to the lecture series on solid state. In this session, we will continue our discussion on a few more problems based on Bragg's equation. We have seen that the Bragg's equation or Bragg's law is given by n lambda equals 2d sin theta, where lambda is the wavelength of the X-rays, d is the spacing of the crystal layers or the path difference, and theta is the incident angle, which is the angle between the incident ray and the scattered plane, and n is an integer with values 1, 2, 3, etc., which is also called the order of diffraction. And in the previous class, we have solved few problems based on this equation. And we have seen that not only the path difference, but if the other parameters are known, we can calculate either the wavelength that we use, of wavelength of X-rays that we use, or the spacing between the planes d, or even the glancing angle or the incident angle. Okay. So, from this equation n lambda equals 2d sin theta, we can calculate the spacing between the planes as d is equal to n lambda by 2 sin theta. And if you have to find out the glancing angle or the incident angle, we can write sin theta is equal to n lambda by 2d. You can also calculate the wavelength from this equation. So, from this we can determine the wavelength as lambda is equal to 2d sin theta by n. In addition, if we get the value of spacing d, from that we can also calculate the edge length of the unit cell. Using the equation, we know that DHKL is equal to AHKL divided by root of h square plus k square plus L square, where h, k and L denotes the indices of the plane and A is the edge length. Okay. So, today let us solve a few more problems based on these equations. The first question is, X-rays of wavelength 0.154 nanometers are diffracted by a crystal. The first order diffraction is observed at 22.5 degree. So, question A, at what angle will the second order diffraction be observed? And B, is third order diffraction possible for this wavelength and set of planes? So, we have two sub questions A and B. For question A, we have to find out at what angle will the second order diffraction be observed. And moving on to B, the question is third order diffraction possible for this wavelength and set of planes? So, let us see how to find out the answer. We will start with the Bragg's law or Bragg's equation, that is n lambda equals 2d sin theta. Now, let us write down the known parameters or given parameters in the question. It is given X-rays of wavelength 0.154 nanometers. So, we have lambda equals 0.154 nanometers. Diffracted by a crystal with the first order diffraction. So, first order diffraction means n is equal to 1. The diffraction is observed at an angle of 22.5 degree. So, that means theta is equal to 22.5 degree. So, we have the value for n, the value for lambda and the angle theta. So, the missing out is d. So, from this equation we can find out d as d equals n lambda by 2 sin theta. So, let us substitute the values. So, that is equal to 1 into the value of lambda is 0.154 nanometers. You can also represent it in meters if you want. Then 0.154 nanometer means that will be 0.154 into 10 to the power of minus 9 meters. Okay. So, for the time being let us represent it in nanometers only. So, 1 into 0.154 nanometers divided by 2 into sin 22.5 degree. So, sin 22.5 degree is 0.3826. So, let us substitute the value. So, we have d equals 0.154 nanometer divided by 2 into 0.3826. So, that will be equal to 0.2012 nanometers. Okay. So, we have calculated the spacing between the planes and we got the value of d as 0.2012 nanometers. Now, we will look at the A part. The question is, at what angle will the second order diffraction be observed? That means, you have to find out the angle theta at which second order diffraction will be observed. So, that means for second order diffraction, we have n is equal to 2. So, how we will find out the angle theta? So, look at the Bragg's equation, we have n lambda equals 2d sin theta. So, from this we can find out theta, that is sin theta. Let us denote the theta as theta 2. So, in order to just convey that it is from a second order diffraction. So, sin theta 2 will be equal to n lambda by 2d. Okay. So, that is equal to 2 into lambda is 0.154 nanometer divided by again 2 into, we got the value of d as 0.2012 nanometer. So, that is 0.2012 nanometer. So, here 2 and 2 will get cancelled off. So, that will be equal to 0.76537. Okay. That means, the value of sin theta will be equal to 0.76537. So, what will be the value of theta? So, theta 2 will be equal to sin inverse 0.76537. So, that is equal to 49.94 degree. So, we have found out the angle at which the second order diffraction will be observed. Okay. So, for that first we determined the spacing between the planes and from that d value we solved for theta 2 and we got the value for theta 2 as 49.94 degree. Okay. Now, we will move on to the B part. So, the B part is third order diffraction possible for this wavelength and set of planes. Okay. So, third order means n equal to 3. So, let us find out the angle. So, sin theta 3, let it be 3 is equal to n lambda by 2d. So, that is equal to 3 into lambda is 0.154 nanometers. So, 0.154 nanometer divided by 2 into d, we got it as 0.2012 nanometer. So, 2 into 0.2012 nanometer. So, that will be equal to 1.148. That is, we got the value of sin theta 3 equal to 1.148. We know that the value of sin theta ranges from 0 to 1. The maximum value of sin theta is 1. So, here we got the value as 1.148, which is greater than 1. So, that means such a third order diffraction is impossible. So, the answer is third order diffraction is not possible for these set of planes and wavelength. Okay. So, we calculated the value for sin theta using the equation sin theta is equal to n lambda by 2d. We substituted the values for n, lambda and d, and we got the value as 1.148, which is greater than 1. So, since sin theta is greater than 1, that is not possible, and hence we can say that the third order diffraction is not possible for these set of planes and this wavelength. Now, we will move on to the second question. Two different X-ray wavelengths with lambda 1 equals 0.0711 nanometer for molybdenum K alpha radiation and lambda 2 equals 0.154 nanometers for copper K alpha radiation are used to study the same crystal. For a certain set of planes, first order diffraction occurs at 8.5 degree for molybdenum radiation. At what angle will the first order diffraction be observed for copper radiation? Okay. So, in this question, two different wavelengths are given. One is for the molybdenum K alpha radiation, the wavelength of the molybdenum radiation, and second one is the wavelength of the copper K alpha radiation. Okay. And it is given that for a certain set of planes, the first order diffraction was observed at 8.5 degree, that is the theta is 8.5 degree for the molybdenum radiation. And we have to find out the incident angle or the scattered angle theta for the first order diffraction observed for copper K alpha radiation. So, let us see how to find out. First, let us write the basic Bragg's equation. We have n lambda equals 2d sin theta. The first part given is with the molybdenum radiation, and for molybdenum we have lambda 1 is equal to 0.0711 nanometer. Angle theta is equal to 8.5 degree. It is a first order diffraction. So, we have n equal to 1. So, from this we can find out the spacing d because that is missing. So, from this equation we can find out d is equal to n lambda by 2 sin theta. So, let us substitute the values. So, that will be equal to 1 into 0.0711 nanometer divided by 2 into sin 8.5 degree. So, when we substitute this, we will get the value for D as 0.24051 nanometers. So, we have calculated the spacing between the planes and the value of D is given by 0.24051 nanometers. Now, what we have to find out? We have to find out the angle with the first order diffraction observed for copper radiation. So, let us find out the angle for the copper radiation. For copper radiation, it is given the wavelength lambda 2 is equal to 0.154 nanometer. Okay. So, using this equation n lambda equals 2d sin theta. From this equation, we have sin theta is equal to n lambda by 2d. Again, n is first order diffraction, so n is equal to 1. So, if we substitute these values, we will get 1 into 0.154 nanometer divided by 2 into the value of D. We got it as 0.24051 nanometers. So, that is 0.24051 nanometer. So, when we substitute all these values, we will get the value of sin theta is equal to 0.32015. So, if sin theta is 0.32015, you can find out the theta as theta will be equal to sin inverse 0.32015. So, that will be equal to 18.67 degree. You can either mention theta or as theta 2, whatever is convenient. So, the value will be 18.67 degree. Okay. So, in this question, you are provided with two different wavelength, one with for molybdenum radiation and the second one with for copper radiation. And using the data given for the molybdenum radiation, we have calculated the spacing between the planes, and from that value we have calculated the angle theta for which first order diffraction will be observed for the copper radiation. Now, we will move on to the third question. First order diffractions from the 100, 110 and 111 planes of cubic NaCl for X-rays from a palladium anticathode are observed at glancing angles of 5.9 degree, 8.4 degree and 5.2 degree respectively. So, what do these observations suggest regarding the type of lattice that NaCl has? Okay. So, we have three different planes. We have a 100 plane, a 110 plane and we have a 111 plane. And the substance given is NaCl, and these the reflections or the diffractions from these planes are observed at angles 5.9 degree for 100. So, for 100 plane, the value of theta, so let it be theta 1 is equal to 5.9 degree. For 110 plane, the diffraction angle, let it be theta 2 is equal to 8.4 degree. Now, next is 111 plane. So, for 111 plane, the angle, diffraction angle is given theta 3 is equal to 5.2 degree. Now, the question is, what do these observations suggest regarding the type of lattice that NaCl has. So, in order to identify the type of lattice that a substance crystallizes, we have to find out the interplanar distance ratio and compare it with the theoretical value. So, what is interplanar distance ratio? We have three different planes 100, 110 and 111. So, interplanar distance ratio means it is the ratio of D100 is to D110 is to D111. So, this is the interplanar distance ratio. So, using this interplanar distance ratio value, we should compare it with the theoretical value for different types of lattices, that is for a simple cubic or body centered or face centered. So, when it matches with any of these lattices, we can say that that substance crystallizes in that particular type of lattice. Okay. So, now here what to do? We have to find out the interplanar distance ratio. Now, let us see how to find out. We have the Bragg's equation n lambda equals 2d sin theta. So, from this d equals n lambda by 2 sin theta. So, if the order of diffraction n and the wavelength of the X-rays used is constant, n and lambda are constant, then we can see that d is proportional to 1 by sin theta. Okay. D is proportional to 1 by sin theta. So, here we have D100. D100 will be proportional to 1 by sin theta 1. Similarly, D110 will be proportional to 1 by sin theta 2 and D111 will be proportional to 1 by sin theta 3. So, similarly, if we take the ratio of these three planes, how can we write? So, D100 is to D110 is to D111 will be equal to, you can write 1 by sin theta 1 is to 1 by sin theta 2 is to 1 by sin theta 3. The values for theta is given. So, you have to find out the sin thetas. So, sin 5.9 degree is 0.1028, sin 8.4 degree is 0.1463 and sin 5.2 degree is 0.0906. So, let us substitute the values. So, this will be equal to 1 by 0.1028 is to 1 by sin 8.4 degree. So, that is 0.1463 is to, so next is sin theta 3, sin 5.2 degree. So, that is 1 by 0.0906. Okay. So, find out the ratio and simplify it. So, that will be corresponding to almost 1 is to 0.705 is to 1.14, and this is theoretically close to the interplanar distance ratio for an FCC lattice. Okay. So, that means we can say that NaCl has a FCC lattice. So, this is how we identify the type of lattice that a crystal belongs to using Bragg's equation. Okay. So, in this 3 different planes and 3 different glancing angles are given and only that data is given. Okay. And from that you have to find out the type of lattice that NaCl belong to. So, we have the equation n lambda equals 2d sin theta, or if other parameters are constant, we can write d as proportional to 1 by sin theta. So, if we find out the interplanar distance ratios, that is d100 is to d110 is to d11, that will give rise to the values which may be either close to simple cubic, body centered or face centered. So, comparing that value with the value of the theoretical, then you can identify which type of lattice that NaCl belong to. So, now we will move on to the 4th question. The wavelength of X-rays is 0.071 nanometer, which is diffracted by a plane of salt with 0.28 nanometer as the lattice constant. Determine the glancing angle for the second order diffraction. Assume the value of the salt plane to be 110 and the given salt is rock salt. Okay. So, here you have to determine the glancing angle or the incident angle theta for the second order diffraction. Okay, let us start with the basic equation. So, we have n lambda equals 2d sin theta. The wavelength of the X-rays is given. So, lambda is equal to 0.071 nanometer. The diffraction order is given as second order diffraction. So, the value of n is equal to 2. It is given that the plane of salt having a lattice constant 0.28 nanometers. So, the lattice constant is A, and A is equal to given as 0.28 nanometer. Okay. So, you have to find out the glancing angle, that is theta, for the second order diffraction. So, from this equation, if we have to find theta, then we can write sin theta is equal to n lambda by 2d. We have n, the value of n is 2. We have lambda, the lambda value is 0.071 nanometer. But in the question, the value of d is not provided. Instead, they have given the value of the lattice constant, that is A is equal to 0.28 nanometer. So, from the lattice constant, you can calculate d. Okay. It is given that the plane is 110. It is a 110 plane. So, using the equation DHKL is equal to A by root of h square plus k square plus L square. So, that will be equal to 0.28 nanometer divided by root of, it is a 110 plane. So, 1 square plus 1 square plus 0. So, that is equal to 0.28 nanometer by root 2. So, from this we will get D110 is approximately equal to 0.198 nanometers. Okay. So, in the question it is given the lattice constant, the value of A. So, from the value of A we have calculated the spacing of the plane D110 and that was obtained as 0.198 nanometers. Okay. Now, let us move on to the second part. We have to calculate the glancing angle for the second order diffraction. So, we have the equation sin theta is equal to n lambda by 2d. So, we can write sin theta is equal to n is equal to 2 into what is the value of lambda? It is 0.071 nanometers divided by 2d. So, 2 into the value of d is 0.198 nanometers. So, we got the value of sin theta as 0.359. So, what will be theta? Theta will be equal to 21.1 degree. So, you can calculate theta as sin inverse 0.359. So, that will be 21.1 degree. So, in such a way we have calculated the angle theta for a second order diffraction. Now, we will move on to the fifth question. The utilized reflecting plane of lithium fluoride crystal has a D value of 2.014 angstrom. Calculate the wavelength of second order diffracted line which has a value of 50.1 degree. So, here we have a lithium fluoride crystal. The D value is given, the spacing D is equal to 2.014 angstrom. Now, in the question it is given you have to calculate the wavelength of the second order diffracted line. Second order diffracted line means n is equal to 2. The angle is also given, theta is equal to 50.1 degree. So, how to calculate the wavelength? We have n lambda is equal to 2d sin theta. So, from this we have lambda, which is the wavelength, is equal to 2d sin theta divided by n. So, let us substitute the values. So, that is equal to 2 into the value of d is 2.014 angstrom into sin theta is sin, the value of theta is 50.1 degree divided by the value of n is 2. So, this will get cancel off. Sin 50.1 degree is 0.766. So, if we substitute in this value, lambda is equal to 2.014 angstrom into 0.766. So, that will be equal to, the value of lambda is equal to 0.1543 nanometers. So, we can calculate the wavelength of the X-rays using this Bragg's equation. Now, we will move on to the sixth question. The first order diffraction of a beam of X-rays of wavelength 15.4 nanometers from the 100 planes of a crystal occurs at an angle of 11 degree 29 minutes. Calculate the distance between the 100 planes. So, here you have to calculate the distance between the planes. the plane given as 1, 0, 0 plane. It is a first order diffraction, so we have the value of n is equal to 1. The wavelength of the X-rays are given, so lambda is equal to 15.4 nanometers. So, lambda is equal to 15.4 nanometers. The angle given theta is equal to 11 degree 29 minutes. So, 11 degree 29 minutes. So, we have the Bragg's equation, n lambda equal to 2d sin theta. So, we have d is equal to n lambda by 2 sin theta. So, when we substitute these values, we have 1 into the value of lambda is 15.4 nanometers divided by 2 into sine 11 degree 29 minutes. So, 11 degree 29 minutes can be converted to degrees like this, that is 11 plus 29 by 60. So, that will be 11.483 degree. So, here it will be sine 11.483 degrees. So, that is equal to sine 11.483 degrees 0.1994. So, substitute that value. So, that will be equal to 15.4 nanometers divided by 2 into 0.1994. Okay. So, this will give rise to 38.6 nanometers. Okay. So, the distance d can be calculated using this equation and the answer is 38.6 nanometers. Okay. So, in a similar way, we can calculate various parameters using the Bragg's equation, n lambda equals 2d sin theta. By knowing the value of d, we can even calculate the edge length of the unit cell, and also by finding out the ratio, interplanar distance ratio, we can also identify the type of lattice to which the substance belongs to. In the next class, we will see a few more interesting topics about X-ray diffraction. Thank you.